Rust has been making waves recently with a series of major updates aimed at cracking down on cheaters. In this video, we're diving deep into the world of Rust to uncover why this game has such a persistent cheating problem and how the developers are fighting back, and what the future might hold for this constantly evolving survival experience. Our journey begins by exploring the roots of the problem. Why does Rust attract so many cheaters in the first place? Well, the first reason lies in Rust's very nature as a survival game with PvP and progression elements. If you play this game, you've likely experienced the frustration of being raided after hours of farming and then losing all your loot to another player. Well, cheating in Rust offers a shortcut, saving time and speeding up progress, making it tempting for those who want to gain an edge without putting in the work. Moreover, at some point, the thrill of Rust isn't just about enjoying the process of farming and grinding, but also about disrupting other players of their plans and their gameplay. The second point requires us to break down the game's history into two distinct eras, Rust Legacy and Rust Experimental, which is the version we all know today. Rust Legacy, the original version of the game, was released in around 2013, laying the groundwork for both the game and its cheating problem. During Rust Legacy era, the game was primarily protected by Valve Anti-Cheat, also commonly referred to as VAC. However, it didn't take long for the developers to realize that VAC wouldn't provide sufficient protection, as it was a minimally invasive anti-cheat system, relying mostly on signature scanning for detection. There was also some form of protection offered by Facepunch themselves, but it was clear that something more robust was needed. By 2016, with the new version of the game, Rust Experimental, the developers made a smart choice by investing in a more effective anti-cheat system known as Easy Anti-Cheat, commonly referred to as EAC. EAC is a more sophisticated solution with various builds depending on the level of investment by the game's developers. And compared to VAC, EAC offers much broader protection with modules operating in both kernel mode and user mode, as well as a solid hardware ID ban system to deter cheaters. The truth is, EAC has worked quite well in Rust up until now. However, it's becoming increasingly clear that as time goes on, the quality of cheats has outpaced the effectiveness of anti-cheats. The reason is simple: it's easier to break something than it is to build it. Another reason for the increase in cheats is the time developers have had to reverse engineer the game's engine. Rust uses the Unity engine, which is built with C#. One of the main reasons it's easier to reverse engineer a game built on Unity compared to other engines like those made in C++ is due to the nature of C# as a programming language. C# is a higher level language, and its code is often compiled into intermediate language, also known as IL, rather directly into machine code, also known as assembly. This intermediate language can be decompiled back into a form that is much closer to the original source code, making it easier for hackers to understand and manipulate. Additionally, tools for decompiling Unity games have been readily available and widely used, further simplifying the process. In contrast, games built with C++ are typically compiled directly into machine code, which is much harder to reverse engineer. The resulting binary code is much more complex and with fewer clues about the original structure and logic of the program, making it significantly more difficult to decipher and exploit. Additionally, Unity is a popular engine, just like Unreal Engine, which allows the knowledge used to create cheats in other Unity-based games to be applied to Rust. If you open GitHub right now and search for Rust cheat, you'll find numerous public examples. However, GitHub is full of viruses, and even the cheat codes that aren't infected often suffer from poor quality, constant crashes, and high CPU usage. And bans from the anti-cheat systems are just one of the problems you'll likely face. Yet, there's always those with minimal knowledge which would take the code, make slight changes, mostly visual, like tweaking the ESP or modifying the menu, and start selling these cheats, further multiplying the number of cheaters. From this explanation, it's clear that up until now, you really did not need any significant expertise to have a functional Rust cheat. A brief tutorial on how to compile a project on Visual Studio's, some help from AI tools like ChatGPT, and some time were all it needed for people to create new Rust cheats daily, massively increasing the number of people cheating in the game. So what have they done to prevent these massive waves of cheaters? Well, on July 5th, 2024, Rust took significant steps to reduce the number of cheaters and, more importantly, to curb the sale of cheats by implementing enhanced security measures. One of these measures was the addition of an obfuscation system similar to SHA-1. Obfuscation is a technique used to make code more difficult to understand, even if someone is able to access it, by applying an algorithm similar to SHA-1, a cryptographic hash function. So basically, the code within Rust becomes much harder to decipher, making it more challenging for cheat developers to reverse engineer the game's logic and create functional cheats. Essentially, it scrambles the code in a way that it hides its true purpose and structure from anyone trying to analyze or modify it. In addition to obfuscation, Rust also introduced an encryption system. Encryption is a method of converting data into a coded format that can only be understood if it's decrypted with the correct key. In the context of Rust, critical data such as game memory and communications between the game client and server is encrypted. This means that any attempts to read or manipulate the game's memory would result in a seemingly only scrambled unreadable data. To bypass this encryption and allow an access of the actual information, cheat developers will need to perform reverse engineering on the game's code to understand exactly how the data is being encrypted or decrypted. This involves figuring out the exact algorithms and keys used by the game, and then recreating these functions within their cheat software. Only as they're successfully replicating the encryption and decryption processes could the cheat gain access to the real usable data. It adds a significant layer of complexity and difficulty than developing cheats, making it much harder to create effective tools for cheating in the game. Together, these two measures, obfuscation and encryption, significantly complicate the process of creating cheats. By making it harder to reverse engineer the game's code and by protecting the game from unauthorized access, these systems act as a powerful deterrent against cheating. And as a result, not only does this reduce the number of overall cheaters, but it also discourages the widespread sale of cheats by increasing the technical barriers to develop them. It's important to note that the encryption and decryption methods added to the game change with each update. And with these changes, it makes it even more difficult for cheat developers to automatically update their cheats, as they must continuously reverse engineer the new encryption processes with every game update. In addition to these measures, Rust also implemented fake fields and fake functions to further complicate cheat development. A fake field is a deceptive piece of data within the game's code that looks like it might be useful or necessary, but it actually serves no real purpose. Its main function is to confuse and mislead anyone attempting to reverse engineer the game. Cheat developers might waste time trying to understand or manipulate these fake fields only to find out they have no effect on the game. This adds an extra layer of frustration and difficulty for those trying to create cheats. In simple terms, it's a fake variable which is never used by the game. Similarly, fake functions are functions within the game's code that appears to perform meaningful operations, but in reality do nothing or serve a misleading purpose. These functions are designed to throw off cheat developers by making them believe they found important code to exploit, when in fact they are dealing with a decoy. This technique forces cheat developers to spend more time and effort analyzing the code, significantly slowing down the development process and reducing the effectiveness of their cheats. These changes in the implementation of new systems focus on complicating reverse engineering demand a higher level of expertise from cheat developers. They made the automation of offset updates, particularly for less experienced developers, much more difficult. As these obstacles increase, the number of cheats available on the market decreases, making it easier for the developers to filter and enforce manual detections on the remaining cheats. Well, what can we expect to be implemented? The developers have already confirmed that a fog of war system will be introduced. To understand why this is significant, it's important to first explain how cheats typically render a player in a game like Rust. In online games, there are two types of processing, client-side and server-side. The server side is where most of the game's logic and data are stored and processed. This includes information about player position, game rules, and interactions. The client side is what happens on your computer or console. It's responsible for rendering graphics, processing user inputs, and displaying the game's world. For a cheat to render a player, it needs access to information about other players' positions. This information is sent from the server to your client so that your game can display the other players in the world around you. Even if a player is far away or hidden behind an obstacle, this data might be still present in your client, just not visible in the game due to normal limitations like distance or line of sight. Cheats exploit this by accessing and reviewing the hidden information, allowing players to see opponents who should be out of sight, giving them an unfair advantage. This is how extrasensory perception, also known as ESP cheats, work. These cheats tap into the client-side data to show the location of all players, regardless of whether they're visible in a normal game view or hidden. The introduction of a fog of war system is a direct countermeasure to this. Fog of war means that your client only receives information about what should be visible to you based on your character's position and line of sight. If a player is outside of your visual range or behind an obstacle, that information won't even be sent to your client. This greatly limits the effectiveness of cheats because there's no hidden data to review. If your client doesn't know about an enemy's position, then the cheat can't know the enemy's position. This change is a major step forward in the ongoing battle against cheating. By restricting the data available on the client side, the developers can effectively prevent many types of cheats from working, as there's simply no information for them to exploit. This approach also means that as the game evolves, it can continue to improve its security by ensuring that sensitive information remains server-side and out of reach of would-be cheaters. However, adding this system to an open-world game like Rust, where players often participate on servers with high ping, this could also be a double-edged sword. The implementation of a fog of war system in such a dynamic environment may introduce various bugs and issues. For instance, players might experience lag, delayed rendering of objects, or even situations where enemies suddenly pop into view due to network inconsistencies. These problems could frustrate players, especially in a game where every second counts in PvP encounters. Moreover, unlike in FPS games like Valorant and CS, which use a similar system, but Rust maps are dynamic. This adds another layer of complexity to implementing a fog of war system. In those FPS games I mentioned, those maps are static and well-defined, making it easier to manage visibility and player interactions. Rust's ever-changing landscapes, on the other hand, makes it much harder to maintain a smooth and consistent experience with this system. While the introduction of a fog of war system could significantly enhance Rust anti-cheat measures, it also comes with potential risks that could impact gameplay. The developers will need to carefully balance these changes to avoid pushing away players who enjoy Rust's open world experience, but only time will tell if these changes will succeed or create new challenges.